Now we present Salient Scientists, words straight from important researchers of the past. First up, by himself, in this part of the show, Charles Darwin. Now, scientists are often misunderstood, being human like the rest of us. Researchers are prone to the same strengths, persistence, enjoyment of discovery, cleverness, and weaknesses, seeing what we wish to see, ego, envy, and jealousy. Yet, as with any occupation, there are skills and mindsets that become baked into one's work through the rigors of the daily grind. Scientists must call for more research. They must learn to use terms like probably and maybe in their writing and their speech. And they must always acknowledge that they do not know everything that can be known on a topic.
As species are produced and exterminated by slowly acting and still existing causes, and not by miraculous acts of creation and by catastrophes, and as the most important of all these causes of organic change is one which is almost independent of altered and perhaps suddenly altered physical conditions, namely the mutual relation of organism to organism. The improvement of one being entailing the improvement or the extermination of others. It follows that the amount of organic change in the fossils of consecutive formations probably serves as a fair measure of the lapse of actual time. During the early periods of Earth's history, when the forms of life were probably fewer and simpler, the rate of change was probably slower, and at the first dawn of life, when very few forms of the simplest structure existed, the rate of change may have been slow in an extreme degree. In the distant future, I see open fields for far more important researches. Light will be thrown on the origin of man and his history. Judging from the past, we may safely infer that not one living species will transmit its unaltered likeness to a distant futurity. And of the species now living, very few will transmit progeny of any kind to a far distant futurity, for the manner in which all organic beings are grouped shows that the greater number of species of each genus and all the species of many genera have left no descendants, but have become utterly extinct. It is interesting to contemplate an entangled bank clothed with many plants of many kinds, with birds singing on the bushes, with various insects flitting about, and with worms crawling through the damp earth, and to reflect that these elaborately constructed forms, so different from each other and dependent on each other in so complex a manner, have all been produced by laws acting around us. These laws, taken in the largest sense, growth and reproduction, inheritance, which is almost implied by reproduction, variability from the indirect and direct action of the external conditions of life, and from use and disuse. A ratio of increase so high as to lead a struggle for life, and as a consequence to natural selection, entailing divergence of the character and the extinction of less improved forms. Thus, from the war of nature, from famine and death, the most exalted object which we are capable of conceiving, namely the production of higher animals, directly follows. There is a grandeur in this view of life, with its several powers having been originally breathed into few forms or into one, and that, whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms, most beautiful and most wonderful have been and are being evolved.
Two of the most important scientists of all time, Marie Curie and Isaac Newton. If you wish to read the latter for the full text from any of the three scholars you've heard from today, the links are in the digital program, or you can go to gutenberg.org and search for them at your convenience.
This piece is an excerpt from Marie Curie's actual speech. Radium is no more a baby. It is more than 20 years old, but the conditions of the discovery were somewhat peculiar. We must go back to the year 1897. Professor Curie and I worked at that time in the lavatory of the School of Physics and Chemistry. I was engaged in some work on uranium rays, which had been discovered 2 years before by Professor Becquerel. I spent some time in studying the ways of making good measurements of the uranium rays, and then I wanted to know if there were other elements giving out rays of the same kind. So, I took up a work about all known elements and their compounds and found that uranium compounds are active, and also all thorium compounds, but other elements were not found active. I took up measurements of minerals, and I found that several of those which contain uranium or thorium or both were active. But then, the activity was not what I could expect. It was greater than for uranium or thorium compounds. Then, I thought there should be in the minerals some unknown element having a much greater radioactivity than uranium or thorium. And I wanted to find and to separate that element. We thought it would be done in several weeks or months, but it took many years of hard work to finish that task. There was not one new element. There were several of them. But the most important is radium, which could be separated in a pure state. As the radioactivity was more strong in some products, we knew that we had succeeded in concentrating the new element. The difficulty was that there is not much more radium in a mineral. We now know that there is not even 1 part of radium in 1,000,000 parts of good ore. And 2, to get a small quantity of pure radium salt, one is obliged to work up a huge quantity of ore. And, well, that was very hard to do in a lavatory. We had not even a good lavatory at the time. We worked in a hangar where there were no improvements, no good chemical arrangements. We had no help, no money. And because of that, the work could not go on as it would have under better conditions. I did myself the numerous crystallizations. And in 1902, I finally succeeded getting pure radium chloride and determining the atomic weight of the new element radium, which is number 226. Now, the special interest of radium is in the intensities of its rays, which is a several million times greater than the uranium rays. And the effects of the rays make the radium so important. If we take a practical point of view, then the most important property of the rays is the production of physiological effects on the cells of the human organism. What is considered particularly important is the treatment of cancer. The radium is more than 100,000 times dearer than gold. But we must not forget that when radium was discovered, no one knew that it would be proved useful in hospitals. The work was one of pure science. And this is proof that scientific work must not be considered from the point of view of the direct usefulness of it. It must be done for itself, for the beauty of science. And then there is always the chance that a scientific discovery may become like the radium, a benefit for humanity. But science is not rich, does not dispose of important means, it does not meet recognition before the material usefulness of it has been proved. So, I am very grateful to the American women who wish me to have more of the radium and give me the opportunity of doing more work with it. The scientific history of radium is beautiful. I hope that we may have some beautiful progress in the following years. It is my earnest desire that some of you should carry on this scientific work and keep for your ambition the determination to make a permanent contribution to science. Thank you.
All right, this comes from a letter from Isaac Newton containing his new theory about light and colors. To perform my late promise to you, I shall without further ceremony acquaint you that in the beginning of the year 1666, at which time I applied myself to the grinding of optic glasses of other figures than spherical, I procured me a triangular glass prism, to try therewith the celebrated phenomena of colors. And in order thereto, having darkened my chamber and made a small hole in my window shuts, to let in a convenient quantity of the sun's light, I placed my prism at his entrance, that it might be thereby refracted to the opposite wall. It was at first a very pleasing divertisement to view the vivid and intense colors produced thereby, but after a while, applying myself to consider them more circumspectly, I became surprised to see them in an oblong form, which, according to the received laws of refraction, I expected should have been circular. They were terminated at the sides with straight lines, but at the ends the decay of light was so gradual that it was difficult to determine justly what was their figure. Yet they seemed semicircular. But the most surprising and wonderful composition was that of whiteness. There was no one sort of rays which alone can exhibit this. It is ever compounded, and to its composition are requisite all the aforesaid primary colors mixed in a due proportion. I have often with admiration beheld that all the colors of the prism, being made to converge and thereby to be again mixed, as they were in the light before it was incident upon the prism, reproduced light entirely and perfectly white, and not at all sensibly differing from a direct light of the sun, unless when glasses I used were not sufficiently clear, for then they would be a little inclined to their color. Hence, therefore, it comes to pass that whiteness is the usual color of light, for light is confused aggregate of rays, imbued with all sorts of colors, as they are promiscuously darted from the various parts of luminous bodies. And of such a confused aggregate, as I said, is generated whiteness, if there be a due proportion of the ingredients, but if any one predominate, the light must incline to that color, as it happens in the blue flame of brimstone, the yellow flame of a candle, and the various colors of the fixed stars. These things considered, the manner how colors are produced by the prism is evident. For, of the rays constituting the incident light, since those which differ in color proportionally differ in refrangibility, they, by their unequal refractions, must be severed and dispersed into an oblong form, in an orderly succession, from the least refracted scarlet to the most refracted violet. And for the same reason it is that objects, when looked upon through a prism, appear colored. For the deformed rays, by their unequal refractions, are made to diverge towards several parts of the retina, and there express the images of things colored, as in the former case, when they did the sun's image upon a wall. And by this inequality of refractions, they become not only colored, but also very confused and indistinct. Why the colors of the rainbow appear in falling drops of rain is also from hence evident. For those drops which refract the rays, disposed to appear purple in greatest quantity to the spectator's eye, refract the rays of other sorts so much less as to make them pass beside it. And such are the drops on the inside of the primary bow, and on the outside of the secondary or exterior one. So those drops which refract in greatest plenty the rays, apt to appear red towards the spectator's eye, refract those of other sorts so much more as to make them pass beside it. And such are the drops on the exterior part of the primary and interior part of the secondary bow. Thank you.